this video, we'll be talking about controllability. And the whole motivation behind controllability relates to designing systems. And that's because for a system to be controllable, that means you can start at any starting point. And as long as you put in the correct sequence of inputs, you'll be able to get to any endpoint that you want, which is really useful when you're trying to make a system do a certain thing. Cool, so now let's dive into what controllability is. So in general, controllability relates to our state space representation. So we usually have the xt plus 1 plus x of t plus b u of t. And there's technically also this like WT term here, which is essentially just noise. But for now, we're going to be considering ideal systems where there is no noise, so we can just disregard that W of t for now. Cool. So this is the general equation for your state space representation. So based on this, we can write like if you start at x of 1, that would just be equal to ax sub 0 plus b u sub 0. And then you can write the same thing for x sub 2. X sub 1 plus b u sub 1. And from here, you can see that you can substitute the value of x1 in, which will then give you a squared x sub 0 plus ab u sub 0 plus b u sub 1. So you can continue writing these equations out and then substituting back in, and you'll ultimately get the form of x of t is equal to at x sub 0 plus at minus 1 b u sub 0 plus at minus 2 b u sub 1 plus so on all the way to b u sub t minus 1. And another way to think about this equation is that specifically in like matrix and vector multiplication form is that you keep this first term, at x sub 0, and then you have a matrix of A, and then you'll have your matrix of at minus 1, b, and then so on all the way to b, and then you'll multiply by u sub 0 all the way to u sub t minus 1. So this, in fact, will be your controllability matrix, which we'll call C. Something to realize is that here we have the inputs u ordered from like input at 0 time all the way to t minus 1. So something to keep in mind is that we usually write this in the kind of flip way where we have b and then ab all the way on to at minus 1b, and then we just flip the inputs. You can see that these two are equivalent. It's just another way of writing it in matrix vector multiplication. So actually, instead of calling this the controllability matrix, we're going to call this form, and we'll see why later on, because in general, it's easier to calculate using this form because you just repeatedly multiply by a as you go left to right, which is just more natural for people to do. Cool. So now we have defined our controllability matrix C. So how you see whether something is controllable or not is you see whether the rank of C is full rank. So if the span of C spans all t dimensions, that it is controllable. Otherwise, it is not. So controllable is equivalent to saying C has full rank, or C has linearly independent columns, or the span of C is equal to all of RT. So cool. So that's what controllability is. And some assumptions to keep in mind and generalizations is that here we have capital B representing a matrix, and that happens when you have multiple inputs. If you only have one input, instead you will just have the vector B. And something to keep in mind is that your B, whether it's a matrix or a vector, should not be equal to 0. So assumptions, B should not be equal to 0, because then otherwise it's trivially uncontrollable, because having the 0 vector will always make it so that it is uncontrollable and linearly dependent. Cool. And we also generally say that the dimension is greater than or equal to 2, because if you have being not equal to 0 and you only have one dimension, then you already know it's naturally controllable since there's only that one vector. Okay, so now we're going to dive into an example to kind of iron in these concepts and see how they would show up in problem form. So cool. So here we have the system. And the first thing we want to do is figure out whether it's controllable or not. And how you do that is by basically writing out the controllability matrix. So we have C is equal to, so you take the vector 2, 0, 0, and then you multiply by A, which I'm going to skip the algebra showing it, but it'll become 0, 0, negative 2. And then you multiply by A squared B, or by A again, and then you will get 4, 0, 0. So this is B, this is AB, and this is A squared B. So here you can see that these two vectors are linearly dependent, so this is in fact uncontrollable. And something to keep in mind is that whenever you add like the next vector into the controllability matrix, it will always at most add one additional dimension, because assuming it's linearly independent. So that means that if you're like calculating your controllability matrix and say this is like 20 dimensions, you don't want to have to be able to calculate like the entire matrix in order to see if it's linearly independent or dependent. So a trick is that if you're like calculating along the way and you get this vector that's already dependent from the previous vector, so it doesn't add a dimension, you know you can stop and say it's uncontrollable already, because there's no way that the rest of the vectors will add any more dimensions to make up for that lost dimension. So once you find one dependent vector, you can stop and directly say it's uncontrollable already. So that's just a trick to keep in mind in order to like limit your calculations more. Cool. Okay, and then let's go to part B. So we know x sub 0 is 1, 0, 0. You want to know the possible states it can reach. So how you do that is essentially by plugging it in. So we have x sub 1 is then equal to the matrix times x sub 0 plus 2, 0 times u sub t. So it would be 2 of u sub 0, 0, 0. And then if you simplify this, you would get 2 u sub 0, 0, negative 1. So from this, you know that what is controllable? It's the input we put in. So in general, we're always controlling the system by whatever input we put in. So since u of sub 0 is controllable, this is essentially like saying you will have like a constant, let's say C1 of some sort, 0, negative 1. So within one time step, you can get it to any vector along this general form. And then you can do the same for 2 time steps, where you will just sub in this as x sub 1 and then into the state space equation. And then x sub 2, you'll get the form of 2 plus 2 u1, 0, negative 2 u0. And this will be at the form c1, 0, c2. For example, and these are just any constant c1s, and notice that these two c1s are different. They're defined within the vector, and then you can do the same thing with x3. And then you will get 4u0 plus 2u2, 0, negative 2 minus 2u1. And then this will be like kind of the same form, c1, c0, and c2. Cool. So usually the next train of thought question is, what's the minimum number of time steps to reach each of these vectors? So let's take 1, 0, 2 first. So we know that this in general is of the form of 1, 0, 2, like it's two constants and then a 0 in the middle. So we know that it can be reachable in at least 2 time steps a minimum, which we can see right here. Because if we go back 1 time step, this bottom term has to be a -1, which is not the case here. And then now let's look at 1, 1, 1. We see from like these 3 time steps, it's not possible to reach this form where the middle term is not a 0. And as we can also see, x2 and x3 already start taking the same form. So it shows that further on, it will not be changeable anymore. And this actually relates to how, since our system is uncontrollable, we actually are not able to reach this vector at all, because we will always stay in the form of a constant, 0, and then a constant.